All right, so let me start, and thanks organizers for organizing this event. So first, let me briefly give you a list of examples where you see non-self-adjoint operators in different branches of science, and probably most of you know better than me, how these non-self-adjoint operators appear in those areas. So I'll not go into the detail of that, but just to let you know that there are many different branches of science and things that you do in different areas there where these non-self-adjoint operators appear naturally. And the problem with this non-self-adjoint operator is that they are very unstable. The spectrum is very unstable. And what do I mean by that? So let's take this very simple example. Let's take this left shift operator on Cn. So in matrix form, it is basically you have this Jordan block where you have zeros on the diagonal and you have 1 on the first super diagonal. So as this is an upper triangular matrix, so you say that all its diagonals are 0, so the spectrum is trivially just a singleton 0. But the thing that one should note is the following, that let's say now I take a Z which is inside the open disk. Let's say my Z is not equal to 0. Then I can show that if I look at the resolvent of this guy, this is Jn minus Z inverse. If you look at the norm of that, that is huge. So this you can check by taking this particular V and compute this Jn minus Z times V, look at the L2 norm of that, and it comes out to be this because of the structure of this matrix Jn. And your V has norm order 1, so you deduce that this resolvent has a exponentially large norm inside the unit disk. But on the other hand, if you take a Z which is outside the closed unit disk, then you can show it needs some argument. You need to show that the operator norm is of order 1 of this resolvent. So this tells us that this inside this open unit disk, for any fixed Z which is away from 0 of distance order 1, you can create a very small singular value, or in other words, you can have the resolvent to be exponentially large in the dimension. So this basically gives rise to following phenomena. So let's say I take this again Jn, I make a small change on the lower left corner. So I put some delta over there, okay? And then you can sit down and check that this Jn delta, its eigenvalues are basically discrete uniform on the circle of radius delta to be 1 over n. So this you can just compute the determinant and you can just reduce it from there. So it basically then means that if I let my delta to be exponentially small in the dimension for some Z in the open unit disk, then this exponentially small perturbation of Jn produces an eigenvalue which are distance of order Z from the spectrum of the original matrix that you started with. And also if you let your delta to be not exponentially small, but delta to be of order 1, or maybe delta to be decaying polynomial in the dimension, then you see that all its eigenvalues kind of as n goes to infinity is being pushed towards the boundary of this unit disk. So you see that this phenomena basically tells you that if you start with a so if you consider any small perturbation, then it is possible to create eigenvalues which are away from the spectrum of the matrix that you started with. Okay, and so now let us build on this idea and order this observation and try to do some fun experiment. So here what we do, we start out with our matrix Jn, we conjugate it to un and un star on the left and the right, and your un is any hard unitary orthogonal matrix or unitary matrix. Okay, then and you ask your favorite mathematical software to compute the eigenvalues of this matrix, new matrix Jn hat. Now you know that conjugating by the orthogonal unitary matrix does not change the spectrum, so you should expect that your the eigenvalues of Jn hat should be close to the eigenvalues of Jn if you do a simulation. But what you see is completely different. So what you see here, that if you start with this your Jn and you do this conjugation, here is n is 1000, then you end up with this picture. So you see that all its eigenvalues are kind of pushed towards the boundary of the unit disk. And this phenomenon is not specific to this particular matrix, it is fairly general. Let me give you some more examples. So if you take this Jn plus Jn square, where you meaning that you put a bunch of ones in the second super diagonal, then you get this shape which is called Limaçon. So then you see that all the eigenvalues of this matrix, or other un times Jn plus Jn square times un star. So we're basically conjugating the matrix that you start with. All its eigenvalues are kind of pushed towards this shape called Limaçon. And again, this is basically is an artifact of the issue is that the spectrum of non-normal or non-self-adjoint operators or matrices here are very unstable with respect to perturbation. And so these are the examples that will come back again. So these are examples of Toeplitz matrices. So I'll define more formally in the next few minutes what we mean by Toeplitz matrices. And this is, this is not just for Toeplitz matrices, it is for holds for more general matrices. So you start from, let's say my matrix is now Hn, where you take this Jn and you add a bunch of diagonals. And these diagonals are uniformly spaced between -2 to 2. So you have this matrix which is again upper triangular, because Jn is an upper triangular matrix and Dn is a diagonal matrix, and all your entries on the diagonal of these guys. Okay, so it means that your spectrum of this Jn is kind of uniformly spaced between -2 to 2. But when you run this experiment that you conjugate this matrix with un and un star on the left and the right, you get something which looks like a stadium. And this kind of matrices that I wrote down here is kind of known in the literature as twisted Toeplitz or Toeplitz variable coefficient, and they have also some other name as well in the literature. So one thing to note, that if you look at the empirical measure of the diagonal matrix, that will be uniform from -2 to 2. Because as you let n go to infinity, they will just approach to the uniform distribution between -2 to 2. And again, a related example. So what you do here, you have a similar looking expression. You take this Jordan block and you add again a diagonal matrix. Now the diagonal matrix has a similar structure. So you put your on a diagonal matrix on independent and ideally distributed distribution, random variable coming from uniform -2 to 2. So again, here you see that if you look at the empirical law of the the diagonal entries, that is uniform -2 to 2, because you are drawing from uniform -2 to 2 for each of those. So you say that this this dn tilde and dn, if I look at the empirical distribution of the the diagonals, or rather the entries of dn and dn tilde, they should be same in the limit. But if when you're doing this new matrix hn tilde, jn plus dn tilde, you see a different picture from the last one. So it's basically something strange happens also here. And as I have been saying, this is basically an artifact of the underlying issue is that the spectrum is really unstable under perturbation for non-self-adjoint or non-normal operators. And this also has a name. This is called non-periodic one-way model. Maybe some of you know. And this is due to Brezin, Feinberg, and Z. And what you see here is sometimes called this Hatton-Nielsen bubble. So, and this is in some way this is limit of Hatton-Nielsen model. So I'll not go into that. Okay. So any questions till now? Yeah.
I have a question. In the Zoom.
In Zoom, okay. Let's go ahead.
Can I use this to somehow characterize how good my distribution of random numbers and some questions like that?
So this I would say is not about the not about these random variables. I mean, so I'm putting this random variable that is true, but this is basically what happens is this spectrum is really unstable. Therefore, when you are doing this computation in the computer, then it produces numerical errors, and because of these numerical errors, you see this kind of things. So that is probably the probably what is on probably what is going underneath this mechanism. Does that kind of answer your question?
Yeah, thanks.
So Anirban, I mean, when you increase the numerical precision of the computer, then of course it should go to the hn tilde, but it's extremely slow. Is that?
No, it is okay. So what happens is that this, so let's say I go back to the simplest example here. So here I think that the precision was like 64-bit. So it does not actually go to 0.
I have a question.
Yeah.
So this un star is the Hermitian conjugate of un.
Yeah.
But did at any point did you claim that after this conjugation the spectrum will change?
No,
like Jn had as a different spectrum.
So the spectrum does not change, but this is what you get when you run a simulation.
I'm sorry, I'm not understanding.
So basically, the spectrum should not change, right? So if you're conjugating with un star, it should not change. But let's say you do this. So you define your Jn in your computer. You ask your software to draw a uniformly random unitary matrix. You multiply by its complex conjugate transpose. Then you ask your computer to compute the spectrum of this guy. Then what you say is this.
Numerical computation artifact.
Yes. And the reason behind that is that this spectrum of these guys is really unstable. this is basically follows from this example that I tried to. So if you perturb your matrix by a very small number here, and you see that it creates eigenvalues on the circle of radius delta to the 1 over n. And if your delta is exponentially small, so here a exponentially small perturbation will also create an eigenvalue which is separated away from the spectrum of a matrix to start with. And what really happens in computer is that when you're doing this kind of computation, the numerical error is generally typically will be polynomial in the dimension. So because of that, you will see this kind of picture.
Sorry, delta is exactly 0. Then what is the spectrum?
So then this is a 0 because you have an upper terminal matrix.
There's only one eigenvalue in the entire spectrum. Only
Yeah.
0.
Yes.
Thanks.
Okay, so let me continue. So, all right. Yeah. So then what we'll discuss in the next 5 minutes or so, I'll try to give you results about what we did over the last few years. Is that try to understand the spectrum of perturbation where it is not a multiplicative perturbation anymore. You just add some perturbation. So you take your matrix that you want to study, then add a small noise, and you want to study what about the spectral behaviors of this additive perturbation of your original matrix. And here using in a simulation. So let's say,
Anirban?
Yeah.
Sorry, can I ask one question?
Sure, go
So
ahead.
in your previous this thing, you had matrix which was empty on the lower half, right?
Yeah.
But what if I have some elements in the lower diagonal, of course, different from the upper diagonal? These things still hold, or
Yeah.
it becomes
Yes.
does it become more stable, or
No, it does not.
it's equally unstable? Isn't
Yeah.
it? I see. Okay, thanks.
So that matrix has to be non-self-adjoint. So if it is self-adjoint, then it is stable. But if it is non-self-adjoint, then it is not stable. Okay, so here what we do in this left panel, what you do, we take this Jn and you add a noise. The noise is a Gaussian. Then you scale the Gaussian by 1 over n so that it is really a noise, meaning that the spectral norm of this matrix that you add is going to 0 with the dimension going to infinity. And on the right hand side, you have this similar picture for Jn plus Jn square. So if you can see that in this, there is this red and the orange concentric circle. So the red is the eigenvalues where you are taking the eigenvalues of this model where you are adding a perturbation, while the orange circle represents the the eigenvalues of this matrix Tn hat, which is basically multiplicative perturbation of Tn. So you see that they are kind of again similar. Okay, so here's the definition of Toeplitz matrix. So what do you mean Toeplitz matrix? You start with a bunch of complex numbers, AIs, and you put A0 on the main diagonal, A1 on the first super diagonal, A2 on the second super diagonal, and so on. And you put A negative 1 on the first subdiagonal, A negative 2 on the second subdiagonal, and so on. And of course, you can view this. Okay, before that, so here I'll only talk about the result when Tn is finitely banded, meaning that there is a band structure along this main diagonal. So as outside that, it is 0, and it is also 0. Okay, and of course, you can view this Tn as a submatrix of an bi-infinite dimensional, bi-infinite operator, and therefore you can view your Tn as a restriction of this operator. And the one thing that goes along with this Tn, this Toeplitz matrix, is a symbol. So if you give me a Toeplitz matrix T or Tn, it could be finite infinite. Then the symbol is basically this bi-infinite series. So it is constructed out of this, this AKs that you put on the diagonals and super and subdiagonals. And if I give you a banded Toeplitz matrix, then it means that this is basically a finite sum. So this is basically a Laurent polynomial. So you run from some negative D2 to D1. You have this sum. And just to give you, this example, and to so in our case, when this Tn is the simplest matrix is the Jordan block, our symbol is just lambda. In the second example that we saw, it is just lambda plus lambda square. And you can see what should happen if you have a general Toeplitz matrix. Now, given this setup, what are the questions that you can ask? So our Tn will be bounded, finitely banded, and n is a random matrix with variance that are of variance order 1. And for example, you can to fix ideas, you can say that they are IID Gaussian entries. And what we'll observe or what we'll study is the spectral properties of Tn plus n to the negative gamma times n. And let me also comment that this gamma has to be at least 1/2, because one can show that the spectral norm of En is of the order n to the 1/2. So you want to make sure that what you're adding is really a noise or perturbation. Okay, and let me I do not have much time. Okay, so I'll just tell you the results of the things that we have done. So what we can ask for, the first question that people ask in the random matrix literature and theory. So you want to understand what is the limit of the bulk of the eigenvalues, meaning that you want to understand what is the asymptotic level density, and you want to understand if this, so let me again go back. So this gamma is often known as the coupling constant, and you want to understand if the limit is, if the limit does not depend on, if the limit does depend on gamma or not. So if it is universal with respect to gamma or not, or also universal with respect to the distribution of the entries of n. And in both these cases, we have found out that it is universal, that it does not depend on gamma, the coupling constant, as well as does not depend on the distribution, but it depends on the symbol. Okay, so okay, let me just briefly tell you what are the results for this particular two examples. I don't have time to tell you the full details. So in the simplest case, the limit, as you can guess, should be uniform on the unit circle. And for the Limassol case, the limit should be the push product of the uniform measure on the unit circle by the symbol. So it is meaning that the limit is just law of u plus u square, where u is uniform on the unit sphere. And then there is a question about outliers, and how do you mean outliers? So you see from the simulation there are some three eigenvalues which does not converge to the support of the limiting measure. And then you want to understand if there is a limiting point process for these outliers. And you can also see from the picture there are no eigenvalues outside this circle, and there is no eigenvalues outside this Limassol. And this can be proved, meaning that you can prove that there should not be any eigenvalues outside the unit disk in this case, that there should not be any eigenvalues outside Limassol in the second case. Okay, and you can prove that there is a limiting point process which governs the law of these outliers. And here this limit does not depend on gamma, but it does depend on the distribution of the entries of n, of the noise that you put. And finally, let me just give you a brief intro or brief description of what we did about the eigenvectors. So here are some plots again. So what are these plots? So I'm looking at this matrix again, this simplest matrix, the Jordan block plus some noise, and I'm looking at the modulo of the entries of an eigenvector of this guy. Okay, and here is gamma equals 2, gamma is 1/2, gamma is 1. So if gamma is 2, you see that it decays very nicely, smoothly. Here also does the same. But for gamma equals 1, something different happens. And if you continue decreasing gamma, if gamma is 0.9, you have this picture, gamma 0.7, you have this picture, and gamma 0.4, you have this picture. So you see that it will become more and more spiky. And what you expect that in this regime where gamma is greater than 1, you will have that your eigenvectors will be localized, and while for gamma less than 1, you will have that your eigenvectors will be delocalized. So I'll stop here. Sorry for going over time. Thanks.
Yeah, thanks, Anirban, for the nice talk. We can at most take one question.
Hi, can I ask a question?
Yeah.
Is there a sense in which gamma can be just complex as well, or
So this gamma can be complex as well. So I would say that it only would so my guess would be that it would only depend on the modulus of gamma. So I think as long as your gamma has absolute value greater than 1/2, it should continue to hold. That would be my guess.
Yeah, and about the change in the eigenvalues that happens when I do multiplication of unitary matrices. If I take the elements of the unitary matrices to be, let's say, numbers like 0.5, 0.25, which requires some finite bits to store them accurately, do I still see the pattern?
Yeah, so this this simulation that I have shown you, that are done for 64-bit, so they're kind of quite accurate for that n. So this phenomenon, this will see, so let's say you're taking n is 10,000. So I would say, so this phenomenon will still be there. This is just an artifact of the fact of the issue is that the spectrum is really unstable. And then as I said that if you have this Jordan block, and if you do a tiny pattern on the lower left corner, and if your delta is again exponentially small, but then so in that case you will still see that your spectrum is kind of pushed away from the 0. This phenomena, this will be there for all large n.
So even if the numbers are powers of 2, like positive or negative powers of 2, all the numbers that I'm using in the matrices.
So this I don't know, but let's say let's want to simulate an uniform distribution, then I don't think that that all the integers will be of powers of 2. So then I don't know what will happen.
Thanks.
Yeah.
So thanks, Anirban, once again for the nice talk.